Episode 4. The First Ocean. Water is life. This is not a poetry or metaphor. It is the fundamental truth of biology. Every living thing we know of, from the smallest bacterium to the largest whale, from desert cacti to rainforest trees, from humans to mushrooms, requires water to survive. Life, at least life as we understand it, is chemistry, and chemistry requires a solvent, a medium in which molecules can move and interact and react. Water is that medium. Water is extraordinary. It is a simple molecule, just two hydrogen atoms bonded into one oxygen atom, and yet it has properties unlike almost any other substance. It expands when it freezes, which is why the ice floats. It has a high specific heat, meaning it takes a lot of energy to change its temperature, which helps regulate Earth's climate. It is an excellent solvent, able to dissolve more substances than almost any other liquid, and it exists in all three states: solid, liquid, and gas, at a range of temperatures found on the Earth's surface. Without water, there would be no life on Earth. Without liquid water, specifically, there would be no chemistry complex enough to produce self-replicating molecules, no metabolism, no cells, no evolution. Dry Earth will be a dead Earth, a barren rock like Mars or the Moon. Interesting to geologists perhaps, but silent and sterile. But Earth isn't dry. Viewed from space, our planet is blue, covered in water, with oceans that hold 1.3 billion cubic kilometers of it. Water is everywhere on Earth. It fills the ocean basins. It flows in rivers and collects in lakes. It falls as rain and snow. It is locked in glaciers and ice caps. It saturates the soil. It is in the air as vapor. It is in the cells of every living thing. Where did all this water come from? How did Earth, formed in the hot inner solar system, where water should have been scarce, acquire oceans? This question has fascinated scientists for decades, and while we do not have all the answers, we now understand the broad outlines of the story. This is the story of Earth's water, of how it came to our planet, of how the first oceans formed, and of what those oceans meant for Earth's future. It is a story that begins in fire and ends in rain. A story of transformation from molten hellscape to a blue world. When we left Earth at the end of the last episode, the planet was recovering from the impact with the collision that created the Moon. Earth's surface was molten, a magma ocean glowing red hot, radiating heat into space. The atmosphere, such as it was, had been largely stripped away by the violence of the impact, and any water that might have been on the surface had been vaporized and lost to space. Earth had to start again, rebuilding itself from the devastation. But even in this devastated not as liquid, but, but as water molecules incorporated into the crystal structure of minerals or dissolved into molten rock. This water had been there since Earth's formation, delivered by the planetesimals and embryos that built our planet, locked away in the interior, waiting as Earth began to cool once more after the Dia impact. Volcanism returned with a vengeance. The entire planet was geologically active, with countless volcanic vents and fissures opening up as the crust formed and reformed. And through these vents, gases poured out from Earth's interior in a process called outgassing. The primary gas released was carbon dioxide, which would have made up a large fraction of the Earth's atmosphere. Nitrogen was also abundant, along with sulfur dioxide, hydrogen chloride, and other volcanic gases. But mixed in with all of these was water vapor, steam released from the magma as it reached the surface and depressurized. This outgassing was the source of most of Earth's atmosphere and oceans. The water we swim in, the water we drink, the water that makes up 60% of our bodies. Most of it came from the inside of Earth, brought to the surface by volcanoes over hundreds of millions of years. But outgassing alone cannot account for all the Earth's water. The inner solar system where Earth formed was hot during the planet building's epoch. Most volatile materials, including water, should have been driven off by the heat of the young sun. The planetesimals that built Earth should have been relatively dry. This is where the outer solar system comes in, beyond the frost line, beyond the orbit of Mars. Temperatures in the early solar nebula were cold enough for the water to condense into ice. Out there in the realm of the asteroid belt and beyond, planetesimals were made not just of rock and metal, but also of ice, and lots of it. Some of these icy bodies, perturbed by the gravity of the giant planets, especially Jupiter, were flung into the inner solar system. Some of them struck Earth, delivering their cargo of water and organic compounds to our planet's surface. We call these icy bodies comets. When they come from the outer reaches of the solar system, and asteroids when they come from the asteroid belt. But the distinction is somewhat arbitrary. What matters is that many of them contained water ice, and when they struck Earth, they added that water to our planet's inventory. The bombardment that we discussed in previous episodes was not just a source of destruction, it was also a delivery system bringing water and the building blocks of life from the outer solar system into the inner planets. Earth was built in part from ice. How much water came from inside Earth through outgassing, and how much came from outside Earth through impacts is still debated. Different isotopic studies give different answers, but the consensus is that both both sources were important. Earth's water is a mixture, a blend of water from the solar nebula that was incorporated into our planet during its formation, and water from comets and asteroids that struck Earth during the late stages of accretion and the subsequent bombardment. Whatever the exact mix, the result was that Earth accumulated a tremendous amount of water, and as the planet cooled after the Theia impact, that water was waiting in the atmosphere, ready to condense. The atmosphere at this time was thick and hot, heated from below by the still warm surface and from above by the greenhouse effect of carbon dioxide and water vapor. The pressure was high, perhaps tens of hundreds of times higher than today's atmosphere, creating a crushing, steamy environment. But the surface was cooling. Heat was radiating into space faster than it was being generated by radioactive decay and residual warmth from the impact. The temperature of the crust dropped, and when it dropped below the boiling point of water, something remarkable happened. It began to rain, not a gentle drizzle, not an afternoon thunderstorm. This was a deluge, a global downpour that may have lasted for thousands, perhaps even millions of years. All the water vapor in the atmosphere accumulated from volcanic outgassing and from the vaporized comets began to condense and fall on Earth. Imagine it, a planet-wide rainstorm with no dry land, no shelter, no pause, rain falling day and night, year after year, century after century, millennium after millennium. The sky dark with clouds, lightning flashing constantly, and thunder, a never-ending roar, and through it all, the rain, hot and acidic, was pounding onto the rocky surface. The rain was hot because the atmosphere was still hot, close to the boiling point, even as the condensation began. And it was acidic because it dissolved carbon dioxide and sulfur dioxide from the volcanic gases in the atmosphere, forming carbonic acid and sulfuric acid. This was not pure, refreshing water. This was a corrosive brew that would have been deadly to any life, had life existed. When the first raindrops struck the hot surface, they instantly vaporized, flashing back into steam. But as the surface continued to cool, eventually from the temperatures drops low enough that the water could remain liquid on contact, bottles formed in low places, in the depressions and the basins of the primitive crust. These bottles grew into pools. The pools grew into lakes, and the lakes, fed by the unceasing rain, grew into seas. Slowly, inexorably, water accumulated on Earth's surface. The first ocean was being born. The early crust of Earth was not smooth or uniform. It was a chaotic landscape of volcanic highlands and low-lying basins, constantly reshaped by continued volcanic activity and the occasional impact from space. The lowest places, the deepest basins, filled first. As water accumulated, it began to cover the seas spread and merged within perhaps a million years, maybe less. Earth had a global ocean, or at least large interconnected bodies of water covering much of the surface. This ocean was nothing like the ocean we know today. It was hot, probably close to the boiling in some places, especially near active volcanic vents. It was acidic from the dissolved volcanic gases. It was sterile, containing no life, no organic molecules of any complexity, just water and dissolved minerals. The ocean was also shallow compared to today's oceans. The total amount of water may have been similar to what we have now, but the ocean basins were not as deep, and there was less continental crust to provide a high, dry land. Much of Earth's surface may have been covered by a relatively shallow sea, maybe perhaps a few hundred feet or at most a few thousand feet deep in most places, and the ocean was opaque, cloudy with dissolved minerals and particulates. The water was not clear blue, but probably murky brown, or green, or gray, depending on what was dissolved in it and what volcanic ash and sediment it carried. But it was an ocean. It was liquid water, vast amounts of it, covering a significant fraction on Earth's surface, and this changed everything. Water is a powerful geological agent. It erodes rock, dissolving minerals, and carrying sediment. It facilitates chemical reactions that would not occur, or would occur much more slowly in a dry environment. And it moderates temperature, storing heat and releasing it slowly, smoothing out the wild temperature swings that would occur in a dry planet. The presence of a liquid water on the Earth's surface meant that weathering could occur. The acidic rain and ocean water reacted with the rocks of the crust, dissolving minerals, breaking down the rock into smaller particles. This weathering consumed carbon dioxide from the atmosphere, locking it in a carbonate minerals like limestone. This is important because carbon dioxide is a greenhouse gas. It traps heat in the atmosphere, warming the planet. By removing carbon dioxide from the atmosphere and locking it in the rocks, the ocean helped to cool the planet even further, creating a feedback loop. More water led to more weathering, which removed more carbon dioxide, which cooled the planet, which allowed more water to condense, and so on. This process, the weathering of rock and the formation of the carbonate materials, would become one of the Earth's primary climate regulation mechanisms, a thermostat that has kept our planet's temperature within a habitable range for billions of years. Without this process, Earth might have become either a snowball, frozen solid, or a hothouse, with runaway greenhouse warming like Venus. The ocean also provided a stable environment where chemistry could occur. In a dry environment on a planet with no liquid water, chemical oceans are slow and limited. Molecules are locked in place, unable to move or interact, but in water, molecules can dissolve and diffuse, coming in contact with one another, reacting and forming new compounds. This is crucial for the origin of life. Life, as far as we know, requires liquid water not just to sustain itself, but to originate in the first place. The complex chemistry that led to the first self-replicating molecules almost certainly occurred in water, whether in the ocean itself, in tidal pools, in hydrothermal vents, or in some other aqueous environment. But we are getting ahead of ourselves. The origin of life is a story for a future episode. For now, we are still in the earliest stages of Earth's oceanic history. Shortly after the first ocean formed, the ocean, once established, began to interact with the solid Earth in complex ways. Water seeped into cracks in the crust, was heated by the hot rocks below, and erupted back out in hydrothermal vents, carrying dissolved minerals with it. These minerals precipitated out of the water when they encountered the cold ocean, forming deposits on the seafloor. Some hydrothermal vents where hot water mixed with cold seawater created chemical gradients that may have been important for the origin of life. We will discuss this possibility in a later episode. For now, it is enough to note that the hydrothermal systems were active on early Earth, as they are today, cycling water through the crust and mantle, exchanging chemicals between the oceans and the interior. The ocean also began to affect Earth's rotation and the tides raised by the moon. With a liquid ocean covering much of the surface, the tidal forces from the moon could move vast amounts of water, creating tides far more dramatic than those we see today. Because the moon was closer and the ocean shallower, these tides may have been hundreds of feet high, crashing onto whatever rocky shores existed, surging in and out twice a day as the moon orbited. The energy dissipated by these tides as water sloshed back and forth further slowed the Earth's rotation, lengthening the day. Above the ocean, the atmosphere was still thick and heavy, dominated by carbon dioxide and nitrogen, with no free oxygen. The sky, viewed from the surface, would have appeared orange or brown light from the young sun, filtered through dense hazy air. There was no ozone layer to block ultraviolet radiation, so the surface would have been bathed into UV light that would be lethal to modern organisms. The climate was probably warm, kept that way by the greenhouse effect of the carbon dioxide in the atmosphere. Some models suggest that early Earth, even with a dimmer young sun, may have had a global average temperature higher than today's, perhaps as high as 150 or 200 degrees Fahrenheit. Though this is uncertain, what is certain that the ocean was warm, cooler than ocean of the Indian, certainly but warmer than today's ocean. In this warm, sterile sea, chemistry was happening. Molecules were forming, reacting, breaking apart, reforming. The ocean was a vast chemical reactor, churning and mixing, driven by currents and tides, and the heat from hydrothermal vents. Somewhere in this ocean, at some point, the chemistry became complex enough to produce molecules that could copy themselves. We do not know where or when or how this happened, and we may never know for certain, but it happened. Life emerged, and once it did, the ocean and the planet would never be the same. But before we turn to the origin of life, we need to address one more aspect of early Earth's oceanic period, the continued bombardment from space. Even after the Dia impact, even after the ocean had formed, Earth was still being struck by asteroids and comets. The bombardment was less intense than it had been during the Indian, but it was far from over. Objects ranging from small rocks to planetesimals miles across continued to cross Earth's orbit and occasionally to strike our planet. When a large object struck the ocean, the results were catastrophic. The impact would vaporize thousands of cubic miles of water instantly, creating a plume of superheated steam that would rise in the atmosphere. The shock wave would have created a tsunami, a wave hundreds of thousands of feet high, that would race across the ocean at hundreds of miles per hour, devastating whatever coastline existed. If the impact was large enough, it could vaporize the entire ocean, or at least a significant fraction of it, returning the water to the atmosphere as steam. This would create a temporary steam atmosphere, incredibly hot and dense, that would gradually recondense over thousands of years as the planet cooled once more. This may have happened multiple times in Earth's early history. The ocean formed was particularly or completely vaporized by a large impact, and then reformed as the water condensed again. Each time, the chemistry of the ocean would have been reset, any complex molecules destroyed, any proto-life sterilized. This raises a troubling question. How could life have originated when a planet that was periodically sterilized by impacts? The answer may be that life did not originate until the bombardment has decreased to a level where the ocean was stable enough for chemistry to progress without being repeatedly reset. There is evidence, which we will discuss in a future episode. That life may have existed early as 4 billion years ago, or even earlier. If so, it must have either originated in an environment that was protected from impacts, such as deep in the ocean or underground, or it originated and was destroyed and re-originated multiple times until the bombardment finally diminished enough for it to persist. However it happened, life did years transform the planet. But we are not there yet. For now, in this episode, the ocean is still young, still sterile, still settling into its role as the defining feature of Earth's surface. Let us take a moment to appreciate what has been achieved. In a few hundred million years, Earth has transformed from a ball of molten rock into a planet with a solid crust, a thick atmosphere, and a global ocean. The conditions for life have been established. The stage has been set. This transformation was not gentle or gradual. It involved catastrophic impacts, including the collision that created the moon. It involved a global magma ocean, cooling and solidifying. It involved centuries of rain, acidic and hot, that filled the ocean basins. It involved volcanism on a scale we can barely imagine, constantly outgassing the interior and reshaping the surface. And yet, through all of this violence and chaos, a habitable planet emerged. A planet with liquid water, with a stable climate regulated by the carbon cycle, with a magnetic field to protect it from solar radiation, with a large moon to stabilize its rotation, a planet that was in every important way ready for life. The ocean is the key to understanding Earth's habitability. Water is the universal solvent, the medium of life, the substance that makes complex chemistry possible. Without the ocean, Earth would be Mars, a dry, cold, dead world with a thin atmosphere and no protection from radiation. But Earth is not Mars. Earth has an ocean, vast and deep, covering 70% of the surface, containing 97% of all the water on the planet. The ocean regulates our climate, drives our weather, sustains our biosphere. It is the reason we are here, the reason life exists, the reason Earth is unique among the planets of our solar system. As we close this episode, think about water. Think about the rain falling outside your window, the rivers flowing to the sea, the ocean, waves crashing on the distant shores. All of that water has been unearthed for billions of years, cycling through the ocean, the atmosphere, the land, and the living things. Some of the water molecules in your body may have fallen as rain on dinosaurs, or cycled through the first cells in ancient seas, or have been locked in glaciers during ice ages. Water connects us to the deep past and to the entire planet. We are, like all life, creatures of water, dependent on it, shaped by it, part of its endless cycle. In the next episode, we will see Earth face one of its greatest challenges, the late heavy bombardment, a period of intense impacts that may have sterilized the planet and reset the clock on the origin of life. We will witness cosmic violence on a scale that makes the Dia impact look like brilliant. And we will see how Earth survived and eventually flourished. But for now, we pause here with the ocean newly formed, calm and sterile, waiting for the chemistry that would lead to life, waiting for the transformation from a geochemical planet to a biological one, waiting for the greatest mystery of all to unfold.